So, in this lecture we are going to talk about how we can find out the weight distribution of a convolutional codes, and we are going to discuss about the distance properties of convolutional code. So, this lecture deals with how we can enumerate the distance profile or the weight distribution of a convolutional code. So, we can define, before we discuss a technique to find out the weight distribution, let us define what do we mean by minimum free distance of a convolutional code. So, minimum free distance of a convolutional code is defined as minimum Hamming distance between two codes v and v hat, where v and v hat are two code words corresponding to information sequence u and u hat, where u and u hat are two different information sequences. So, it is basically free distance is the minimum Hamming distance between any two code words in a convolutional code, and this is same as minimum weight non-zero. So, it is a minimum weight of a non-zero code word. We know that performance of any convolutional code depends on its weight distribution, and that is why we are interested to find out what is a weight distribution of a convolutional code. In this lecture we are going to talk about a method based on Mason's gain formula to compute the weight distribution of a convolutional code. So, in this we are first going to modify the state diagram of a convolutional code. And how are we going to modify the state diagram? We are going to split the all 0 state into two states, one initial state and second final state, and we are going to remove the self loop around the all 0 state. Next, each branch which is linking from one state to another state, this branch will be labeled by the output weight of the code words. So, we are going to denote by x raised to power I, where I will be the weight of the coded bits. So, for example, if we make a transition from state 0 to state 01, when an input 1 comes and the output is 1 1. So, in that case, since output is 1 1, we will label that branch by x raised to the power 2. So, now after we split this all 0 sequence, all 0 state into two states, initial state and final state, what we will have is each path starting from this initial state to the final state, that will be our valid code word. So, each path connecting the initial state to the final state is a valid non-zero code word, because we have removed the self loop around the all 0 state. So, this modified state diagram is now going to show us all possible non-zero code words. We define a path gain as product of branch gains along a path, and the weight of a code sequence will be nothing but the power of x in the path gain of the corresponding path, because what we are doing is, so each branch is labeled by its corresponding output weight. So, if we look at each path going from the initial state to the final state and we look at the power of x, that will give us the overall weight of that particular non-zero code sequence. As we said, we are going to use Mason's gain formula to compute the weight enumerating function for the convolutional code. So, we are going to describe how we are going to use the Mason gain formula. So, we are representing by T of x the generating function, which will basically enumerate all code words of weight I. Now, let us define few terms that we are going to use in Mason's gain formula. The first term that we are going to define is what is known as forward path. So, a forward path is a path from the initial all 0 state to the final state, and the condition is this path should not go over any state twice. That is our forward path. Next term that we define is basically a loop. What is a loop? A loop is a closed path that starts and ends in the same state without going over any state twice. That is a loop. When do we say two loops are non-touching? We say two loops are non-touching if they do not have any state in common. So, again I repeat these three definitions. Forward path is a path from initial state to the final state without visiting any state twice. A loop is a closed path starting and ending at the same state without going over the same state twice, and two or more loops are non-touching if they do not have any state in common. Now, let us denote by f sub I the gain of the ith forward path, and let Ci denote the gain for the ith loop. We denote by this the set of all loops. Similarly, this set of I and j will denote set of all pairs of non-touching loops. This triplet will define set of all triplets of non-touching loops. So, if we use this, we define a term delta, which is defined as follows. This is 1 minus summation of all the gains of the loops plus product of gains of all those non-touching loops minus this is product of set of all triplets of non-touching loop, and it goes on like this. So, that is our delta. We define our graph that is obtained after we remove all states belonging to an ith forward path by G sub I. So, G sub I is basically the graph remaining after we remove the ith forward path, and the delta corresponding to this modified graph will be denoted by delta I. So, the Mason gains formula then says that the generator function for this convolutional encoder can then be given by this expression. So, this modified state diagram can be augmented to include more information. Now, what we had done so far was we labeled the branches of this state diagram by the overall total weight. Now, we can also augment this by mentioning what is the input that results in that output weight. So, we can label the weight of the input by y. So, the power of y will denote what is the input weight, and similarly we can label each branch by z. So, in a path gain formula, the degree of z will tell us like what is the length of non-zero path. So, the degree of z will tell us, like once it diverges from all zero state, after how much time it comes back into all zero state. So, we can augment our state diagram by what I call a modified state diagram by adding two additional information. One is the weight of the message bit, which will be denoted by power of yi, and other is branch, which will be denoted by z. So, we can then similarly define an augmented transfer function, which will not only tell us the code word weight, but it also tell us what is the input weight that results in that particular output weight, and it will also tell us length of that particular code word. By length I mean the time it diverges from all zero state until it comes back to all zero state. So, this is basically what we call input output weight enumerating function, because this function is enumerating for what input you get what output. Okay. So, this will give us weight input output weight enumerating function, and it is a property of the encoder. An alternative version of this input output weight enumerating function is one that contains only information about the input and output weight and not the length of each code word. So, if we put z equal to 1, basically this is going to give us, it is an alternative version of input output weight enumerating function. And what is weight enumerating function? The weight enumerating function will only tell us what is the overall code word weight, and this is a property of the convolutional code. So, weight enumerating function is related to input output weight enumerating function in this particular way. So, if we put z and y as 1 in the input output weight enumerating function, we will get back our weight enumerating function. Similarly, we can define what is known as conditional weight enumerating function. So, what is conditional weight enumerating function? The conditional weight enumerating function, it enumerates weights of all code words associated with a particular information weight. So, if you are interested in knowing what is the output weight, corresponds to weight for input sequence. So, from the input output weight enumerating function, by collecting all terms which will have W4, we can find out what is the weight of all code words corresponding to output weight, input weight of 4. And again we are using y to denote the input weight. So, if you are interested in input weight 4, we should look for terms containing y raised to power 4. So, this denotes the input weight, this denotes the output coded weight, and this denotes the length. So, as I said, for an input weight of j, conditional enumerating function will give us what is the output code weight that you can achieve for an input weight of j. And we can write our input output weight enumerating function in terms of conditional weight enumerating function. So, this is basically input of weight j will result in conditional weight enumerating function, and we show it for all j's, that will be our input output weight enumerating function. This is another property which is defined for systematic encoders, which is called input redundancy weight enumerating function. So, here because the output weight of a systematic encoder consists of weight of the information bits and weight of the parity bits. Now, since the power of y already is denoting the weight of the information bits. So, when you are asked to show the output weight, you can just, instead of saying the output weight, you can just specify the weight of the parity bits, because it is a systematic encoder. The overall weight will be weight of the parity bits and weight of the information bits. So, overall weight would be W plus G. So, input redundancy weight enumerating function is defined for systematic encoders. So, where instead of specifying the overall coded weight, here you only specify the weight of the parity bits. Now, let us take an example to illustrate how we can find the weight enumerating function of a convolutional code. So, we are going to consider a rate 1 by 2 convolutional code whose memory is 2. So, this is the convolutional code. We can see basically VL1 is UL plus UL minus 2 and VL2 is nothing but UL plus UL minus 1 plus UL minus 2. This is our convolutional code. Now, the state diagram for this convolutional encoder is given by this. Now, we are going to modify this state diagram for the purpose of calculating the weight enumerating function. So, recall what are the modifications we have to do. We have to remove this self loop around the all 0 state, and we have to split this all 0 state into 2 states, initial state and final state. Next, we have to label all these branches by weight of the output bit. So, this will be x2, this will be x0 which is 1, this will be x, this will be x square, this will be x, this will be x, this will be x. If you go back, this is how my augmented, well, modified state diagram will look like. So, what I did was, I have these states here, I split this all 0 state into 2 states. So, this state was split into initial state and final stage. Okay. Next, what did I do? I redrew the same diagram, but I labeled each transitions by the weight of the output. So, you can see from 0 0 I am going to 1 0 and its output weight is 1 1, which is x square. So, let us go back here, from 0 0 I am going to this state and output is x square. This branch is labeled by x square. Similarly, you can see from, let us say, from this state you are going to this state and the weight is x. You can see from this I am going to this state and the branch is labeled by x. Okay. From this state you are going to this 1 1 state and the branch is labeled by x. From this you are going to this 1 1 state and it is labeled by x. Around this state 1 1, there is a loop which has weight 1 x. So, this is my loop around 1 1 which has weight x. So, like that basically we modified the state diagram, and this is how our modified state diagram of a RAID 1 by 2 convolutional code that we just showed looks like. Okay. Now, the next step is we need to find out what are the forward paths, what are the loops, what are the non touching loops, and then we need to find out the path gains along those forward paths. We need to find out deltas corresponding to these forward paths, and then we need to apply Mason's gain formula to get the weight enumerating function. So, first we find out what are the loops. So, there are 3 loops in this. One is a self loop around this state S3. You can see there is one loop, right. There is another loop, right, and then there is another loop. So, there are 3 loops here, and that is what I am denoting it by S3 whose gain is x. Next one is S1, S2, S1. S1, S2, S1 is this one, okay, and the third loop is given by this. So, these are the 3 loops, and corresponding to these 3 loops, these are the gains. Next, what are the pair of non-touching loops? Now, only these 2 C1 and C2 are non-touching loops. You can see, again go back to this example. This loop and this loop are non-touching. Why? This loop contains S3 and this loop contains S1 and S2. So, they do not have any state common between these 2 loops. So, the set of non-touching loops is basically this C1 and C2, and the gain corresponding to them is basically x square. And there is no set of 3 loops which are non-touching. So, now we can then find out the value of delta, which is 1 minus summation of these loop gains and plus set of non-touching loops. So, this comes out to be 1 minus 2x. Next, we are going to find out what are the forward paths. So, there are 2 forward paths in this, and we are going to show you. So, let us use a different color pen. Let us use a red color pen. Remember, what is a forward path? A path from the initial stage to the final stage without going over any state twice. So, one forward path is this, fine. What about another forward path? The another forward path is this. Both the cases you can see I am not going over any state twice, and there are only 2 forward paths in this case. And what are their corresponding path gain? For the one which I marked with red, this is x square x and x square. So, this will be x raised to power 5, and this will be x square x x x square. So, this will be x raised to power 6. So, then we have 2 forward paths, the one with gain x 5, another with gain x 6. Now, what is the next step? We need to remove the forward path and see what is the graph remaining, and we need to compute the delta corresponding to that. Now, again let us go back to the same diagram. If I remove this forward path, what is left in the graph? Only this node. So, only this is remaining. And what about if I remove this forward path? If I remove this forward path, everything is gone, there is nothing left in the graph. So, that is what I am saying here. If I remove the forward path 1, the only graph remaining is this, and the delta corresponding to this is basically there is only one loop with gain x. So, this is 1 minus x, and for the second case there is no graph left. So, delta 2 will be 1. Okay. So, now I have f1 delta 1, f2 delta 2 and I also have the value of delta. So, I can then apply Mason's gain formula to get the weight enumerating function. So, the weight enumerating function is given by this expression. So, I plug in the value of f1 delta 1, f2 delta 2 and delta, and what I get is this expression, which I can write like this. So, you can see basically my output consists of one code word of weight 5, two code words of weight 6, 4 code words of weight 7. So, you can see this transfer function is completely enumerating the weight distribution of my convolutional code. And the same thing I can do with augmented transfer function. And again, because the minimum weight is 5, so free distance of this convolutional code is 5. Now, we repeat the same exercise with the augmented state diagram. Now, what was augmented state diagram? Each valid branch we added a Z to denote this. You can reach from one state to another in one step, and we also added in each of these branches the weight corresponding to the information bits. So, if the information bit weight was 0, so y 0, so that was 1. So, you can see in some cases the information sequence weight is 0. So, let us just go back to the original state diagram. Yeah, let us go back to this. So, you can see for this transition from 0 1 to 0 0, what is the weight of the information sequence? That is 0. So, y 0, that is basically 1. What about this? The weight of the information sequence, here the input is 1. So, this will be y. What is the weight of information sequence? That is 1. So, it will be y. This is weight of information sequence is 0. So, y 0 is 1. So, wherever you had 1 here, you are adding basically y. This is 1, and similarly at each of these transitions there will be a z added to denote the length. Okay. So, that is your augmented state diagram, and that is what I mean, the completed augmented state diagram is what I am showing you here. This is basically my augmented state diagram, where I am not only specifying the coded weight, but I am also specifying what input causes that output bit and z to denote the length. And I follow the same procedure using Mason's gain formula to compute the weight enumerating function. So, I get this information. I am skipping the steps, it is exactly the same procedure I just laid out for computing the weight enumerating function, and you can see it gives us lot more information. The weight enumerating function said we had one code word of weight 5. Now, it says that code word of weight 5 basically was caused by message information bit 1 and the length of the digression from all 0 state before it merged with all 0 state was 3. Similarly, there we had shown that there were 2 code words of weight 6. This completely specifies what those 2 code words was. One which was generated by message bit weight 2 of length 4, this was message bit 2 length 5. So, you can see the augmented state diagram, if we use it to generate a transfer function, it gives us lot more information. So, with this I will conclude this lecture. Thank you.